Orchestrations should feel pretty familiar to you by now. You've seen how we can use orchestrations to control the message flow within our applications. You've seen how we can define ports to create message entry and exit points for our orchestrations. You've seen how we can even communicate with other orchestrations using the call orchestration shape and the start orchestration shape. So with those capabilities, our orchestrations could probably handle most of the common integration scenarios that we might encounter. There are still a few scenarios, however, that could prove difficult if we ended our discussion here. One of the examples that has come up from time to time is the possibility that our orchestration might need to send an email. So fortunately, BizTalk can help us deal with that. And while it's true that the call orchestration shape and start orchestration shape can help us interact with other orchestrations, we know that the limitation of the call orchestration shape is that it's a synchronous call, and while the start orchestration shape makes an asynchronous call, we haven't talked about a way that it can communicate back with its caller. So we'll talk about a few different ways to establish more flexible communication between orchestrations. And finally, we also need to talk about the possibility of our orchestration receiving multiple messages that are all related. And we may not know the number of messages or the order in which they arrive. And fortunately, BizTalk can help us deal with that as well. In the process of creating our orchestration ports, we have been consistently selecting the binding option known as Specify Later. In the first part of this module, we're going to talk about other binding types that will allow more flexibility in the ways that we could use our orchestration ports. In the second part of this module, we're going to revisit the concept of correlation, and then we'll talk about some additional considerations that we need to keep in mind when we implement correlation and allow our orchestration to receive multiple messages that are related. Okay, well, let's get started by talking about how we can apply these other binding types to our orchestration ports. We have already talked about the Specify Now and Specify Later binding types. So the two binding types that we will be talking about here are the dynamic binding type and the direct binding type. We're also going to talk about how we can assign specific ports to different trading partners, and then we're going to use something called role links within our orchestration to interact with those ports. Well, it's not too hard to come up with scenarios in which an orchestration needs to set a destination URL at runtime. The example of an orchestration initiating an email has come up a few times already, but it's also possible that our orchestration might need to dynamically create a URL for other protocols as well. It might, for example, have to format an FTP URL that includes a folder name that is based on the current date. Another possibility is that it might need to format a custom query string for an HTTP URL. It's even possible that the protocol itself might not be known until runtime. Well, fortunately, we can apply the dynamic binding type to orchestration send ports to handle these types of situations. Now, the way in which your orchestration determines the destination URL is up to the design and the requirements of your application. The value might come from a field in a message. Your orchestration might call a helper method that does a table lookup. Or the URL might even be set by a business rule. However it goes about it, the orchestration ultimately needs to determine the URL and assign that to a property on the dynamically bound port. Now, while you set the destination URL on the port itself, you can set additional properties on the message context that can be used to configure the send adapter. If the message will be sent by email, for example, you could set the subject line. If an FTP location requires authentication, the orchestration could set the username and password in the message context. And since each adapter defines its own set of message context properties, you'll need to make sure that the orchestration sets the message context properties that correspond to the adapter specified by the URL. And then beyond just setting adapter properties, it's possible to set configuration data for pipeline components. So, while it's easier to maintain static ports if a message will always be sent to the same URL, When you do encounter a situation in which the URL won't be known until runtime, the dynamic binding option should give you the flexibility that you need to fulfill the requirements of your application. Now, there's an assumption that is common to all of the binding styles that we've talked about so far, and that is that each logical port in our orchestration will be bound to some physical port. Even in the case of dynamic binding, while the physical port might be configured at runtime, there is still a direct tie between the orchestration's logical port and that dynamic physical port. If you recall from our earlier discussion of orchestration ports, when a message passes through a physical receive port, the unique ID of that physical receive port is written to one of the message's context properties. And when we bind an orchestration's logical port to that physical port, one of the conditions for that orchestration port's subscription checks for the unique ID of the physical receive port. And on the outbound side, when a message is sent through a logical send port, the orchestration runtime will assign a message context property with the ID of the physical send port that should transmit this message. Now we're going to talk about a binding style that does not assume that our logical ports will be bound to physical ports. When we choose direct binding for a logical receive port, the subscription for that port will not include a condition to check for the unique ID of any physical receive port. And when we choose direct binding for a logical send port, the orchestration runtime will not insert the unique ID for any physical send port. So direct binding then is going to give us some flexibility that we didn't have before, but it raises two questions. The first question is, why would we want to use it? And then the second question is, what do we need to do about our orchestration's subscriptions now? Well, the short answer to the first question is that it gives us new options for coordinating communication between orchestrations. And there are other benefits as well, but I'll talk more about those as we move on. And the answer to the second question is that there are three different ways that we can deal with our orchestration's subscriptions. In other words, there are three ways to implement direct binding. The first option is to bind directly with the message box. And in that case, it's up to you to define the subscription conditions. The orchestration designer will give you a little more help if you choose either of the other two options. And those are known as self-correlation and shared ports. So let's take a closer look at each of these direct binding options. Of the three options, the first one, that is binding directly to the message box, offers the most flexibility, and it shouldn't come as any surprise that it's going to require more attention to detail than the other two options. We are, after all, taking almost complete control over the way in which an orchestration port interacts with the message box. When we bind orchestration receive ports directly to the message box, we will need to specify filter conditions on the corresponding receive shapes in order to define the subscription conditions. And when we have orchestration send ports that are directly bound to the message box, we will need to ensure that the message being sent has its message context populated correctly. And we need to keep in mind that just because the orchestration has populated some context properties and has sent the message, does not mean that there's necessarily a subscriber for that message. In the event that there is no subscriber, the orchestration will receive an exception. So the design of our orchestration will need to account for that. Now on the receive side, you already have some experience setting up filter expressions. And you might have discovered that they can be a little tricky to get right. And that's no less true here. You need to be particularly careful if your orchestration receives a message of a certain type, and it publishes a message of that same type back to the message box. You will need to make sure that your filter condition distinguishes between messages that have already been processed by the orchestration and messages that haven't. Otherwise, you could end up with something like an infinite loop, in which your orchestration keeps processing the same messages that it is publishing. One of the really cool things about using ports that are bound directly to the message box is that correlation works no differently than what you've seen already. You initialize a correlation set in a send shape, and you configure a receive shape to follow that correlation set. Just as before, an instance subscription will be created when a message is sent. The only difference here is that that instance subscription will not include the unique ID for some physical port. And that would allow another orchestration to process the message you've sent and publish a response back to the message box. And the only requirement there is that the response message must have the properties that are required for the correlation promoted to the message context. And that's a really nice pattern because that allows you to implement two-way asynchronous communication between two orchestrations. Finally, one last point to consider with regard to this type of direct binding is that it gives you a way to maintain loose coupling within your application. And that will make it easier to add and remove components in your application as you need to make modifications down the road. Your orchestration, after all, is just interacting directly with the message box, and it really doesn't know what type of component has published the messages that it is receiving, nor does the orchestration know what type of component processes the messages that it publishes. So, a business function that is implemented as an orchestration today might be implemented as a web service call through a send port sometime in the future. As long as the new send port subscribes to the same properties as the orchestration that it's replacing, it may be possible that no further changes are required. The second direct binding option uses something called self-correlation. And that name stems from the fact that we're going to rely on an orchestration port to handle the correlation for us. In other words, we expect that the port itself will take care of all of the correlation details. You might recall from our earlier discussion of the start orchestration shape that it's possible to pass in parameters into the orchestration that is being invoked. But since the start orchestration shape implements an asynchronous call, that shape won't allow us to receive any parameter values back. Well, that would be a pretty severe limitation if we could never receive information back from an orchestration that we invoked asynchronously. Fortunately, this direct binding option provides a way to implement two-way communication between orchestrations that are executing in parallel. You can set this up by creating a direct bound receive port in the orchestration that will be initiating the call, and then pass that as a parameter via the start orchestration shape. And that will allow the first orchestration to continue executing while the second orchestration initializes and begins executing. When the second orchestration reaches a point at which it is ready to pass information back to the first orchestration, it can simply send a message through that port object that it received when it was initialized. From the second orchestration's point of view, it will see that logical port as a send port. And there's nothing to say that you're limited to creating one of these types of ports. This pattern can start getting pretty sophisticated if you pass a port that defines multiple operations, or if you pass in multiple port objects. Particularly if you take advantage of the fact that you could pass in send ports, receive ports, and two-way ports. Well, you might say at this point that it sounds like we're establishing tight coupling between those two orchestrations. And agreed, the potential is there. There's nothing to say, by the way, that we couldn't implement multiple orchestrations that could accept these ports as parameters. If we had that type of scenario, our first orchestration could decide at runtime which of the secondary orchestrations it needed to call, and then execute down a branch of code that invokes the appropriate orchestration. So the main limitation here is that the first orchestration needs to invoke the secondary orchestration by name. On the other hand, this type of binding is especially useful if you don't have a message property that you can use for correlation. Since the orchestration runtime is handling the correlation for you here, you don't need to be concerned with those details. The orchestration runtime will actually generate a unique ID that it will use to implement the correlation. The third direct binding option makes use of shared ports, also known as partner ports. And this option fully encapsulates the details of the direct binding. It handles all of the details related to the subscription and any correlation that's involved. With this option, you declare right up front as you're creating the direct bound port which two orchestrations will be sharing it. And then the shared port will appear as a receive port in one orchestration and as a send port in the other. So, since the connection between these orchestrations will be established at design time, it would require recompilation if you were to make any modifications to that connection. When we looked at dynamic binding, we saw that an orchestration could have almost complete control over the configuration of a send port. And sometimes you need that, especially when you're dealing with a scenario in which you need to send emails to individuals. It could get kind of expensive, however, if we had to implement all of the details of dynamic binding anytime we needed to select a destination URL at runtime. Beyond that, as powerful as dynamic binding is, we don't have complete control over the send port. We cannot, for example, specify a service window. And if we stop that send port in the administration console, all of the messages being sent through it will be queued. And that might not be what we want. We might only want to stop messages that are being sent to some given destination URL and allow all of the others to be sent. So it would be nice to have the option of something more flexible than a static send port, but a little bit easier to manage than a dynamic send port. And that's exactly what BizTalk's role links are intended to address. You could think of a role link as a placeholder for a port. And when we use a role link instead of a dynamically bound send port, the orchestration no longer has to provide all of the configuration details. It simply needs to provide a name or ID to specify the recipient of a message, and the BizTalk runtime takes care of the rest. Now, as you might expect, there are a few things going on behind the scenes here. For one thing, the send port configurations for the various recipients must exist somewhere. And those actually do exist as individual send ports that show up in the admin console. Each of those send ports, however, is associated with something known as a party that identifies the recipient. Most often, people think of parties as trading partners, but there's nothing that stops you from creating a party that represents another business unit or a system within your own organization. Each party has one or more identifier values associated with it. There will always be one identifier called organization name, and that's just a string value. And then it's up to you to decide if you want to provide any other identifiers. And that could be a phone number or an email address, or it might be some other identifier that your organization has defined. Once you have your parties set up and you have specified which send ports belong to each party, when you deploy your orchestration, you will need to click on the Role Links node in your application and specify a list of parties for each role link that your orchestration will be using. Let's step through this animation to get a better understanding of how all of these pieces fit together. As our orchestration is executing, it is going to reach a point at which it needs to select a shipping vendor for the order that it is processing. You can see in the upper right that we have 3 shipping partners identified, and each of those partners has a send port associated with it. Our orchestration will very likely call a business rule policy to determine which shipper should handle this order. Once it determines that value, that orchestration is going to set a property on the role link identifying the chosen shipping partner, and then it will send the message to the role link. At that point, the BizTalk message engine is going to perform a lookup based on the ID that the orchestration provided, and it will compare that against the identifiers for all of the parties that are associated with this orchestration role link. Assuming that it finds a party associated with that identifier, the message engine will determine which of the party's send ports has been associated with this role link, and then it will send a message to it. So by using role links, the orchestration only needs to know how to identify a party, and it doesn't need to be concerned with any of the details regarding the send port configuration. The last thing that we need to talk about is what an orchestration needs to do to get or set the party for a role link. On the send side, it will need to initialize a new party object, and then it will need to provide the value of one of the party's identifiers, and then it will need to provide the qualifier that indicates what the identifier value represents. In the line of code that you see at the bottom of this slide, the first argument in the party constructor could be the name of one of our shipping vendors, such as FedShip. And then the second argument would correspond to the organization name that we specified for this party when we created it in the administration console. And then we need to assign that new party object to a property of the role link known as the destination party. So this line of code assumes that our orchestration has a role link called the trading partner role link. And then your orchestration will need a way to determine the correct destination party, whether it simply reads a property from one of the messages that it is processing, or calls a business rule policy, or it might use a helper method that you provide in a class library. So however it goes about it, once it initializes the party object and assigns it to the role link, the BizTalk runtime will take it from there. Now in this discussion of role links, I have been focusing mostly on the send side. On the receive side, you can make use of the party resolution pipeline component to identify the party that sent a message into BizTalk. The party resolution component could, for example, identify the sender by the Windows username that was provided to authenticate with IIS. If the party resolution component is able to determine who sent the message, then you'll be able to see the name of that party in a message context property that is named source party. This will only work, by the way, if the receive adapter is running in a host that is marked as authentication trusted. So if these messages are arriving through IIS, you would need to check the trusted checkbox on the corresponding isolated host. Here's a quick summary of all of the binding options that we've just talked about. You can bind directly to the message box if you want to take full advantage of the publish-subscribe architecture, but you'll need to think carefully about how your application will be using subscriptions. And you need to think about that both from the perspective of publishers and subscribers. If your application will be sending messages to such a wide array of destination URLs that it's not practical to define a send port for each one, then you'll want to think about using dynamic addressing, or what the orchestration designer refers to as dynamic binding. If you just need to establish asynchronous communication between orchestrations, then you might consider using self-correlating ports. Or you might think about using a shared port as well, provided that the tighter coupling that it implies doesn't pose any issues with regard to your application design. And finally, if your orchestration will be communicating via a well-known set of URLs, then it might make sense to think about using role links. In this demonstration, I will walk you through an orchestration that makes use of dynamic addressing to send an email, and it also uses a role link to specify which shipping company should be used to deliver an order. And then in the BizTalk administration console, I will show you the configuration for each of the parties and how they are associated with the role link. In this demonstration, we're going to concentrate on the order processing orchestration and look at the way that it uses dynamic binding and role links to route messages to the correct destination. All right, the order messages will arrive through this receive port. And then the decision shape checks the country listed in the shipping address. And if the order is to be shipped to the UK, then the orchestration will map that to a shipping message and send that message on. And we'll come back to this branch of code to look at it more closely. If the order will not be shipped to the UK, then the orchestration needs to construct a billing message and send that out via email. So this message construct shape is going to set up the billing message, and then it will be setting some properties to configure the email. This first line is simply going to copy over the body of the message, and then this is going to copy over all of the message context properties, And then the code is going to set the subject line for the email, as well as the text of the body of the email, and indicate the character set that's used. And this line is indicating that the SMTP adapter will be adding one attachment to this email. And the file name of that attachment will be set to billingrequests.xml, and the attachment itself is going to be XML content. So as the message is being passed through the SMTP adapter, the adapter will read out these properties and make use of them to format the outbound email address. The email address itself is set as a property on our dynamically bound port. And in this case, that port is named billing port. So that is simply hard-coded in this expression shape. In reality, you might have called a helper class to determine this address, or you might be using a variable that was set by a business rule policy. Okay, let's take a look at the billing port itself. Since the billing message is simply a copy of the order message, the billing port is of the order port type. And then the critical characteristic is the port binding. You can see that the billing port is configured to send messages, and that the port binding type is dynamic, and it makes use of the pass-through pipeline. Alright, well that takes care of the dynamically bound port. Let's revisit the other branch of code and look at the role link. In this case, our orchestration has a role link named shipper role, and we're going to set the destination party property on that role link. And to do that, we need to create a new party object. And we're going to initialize that party object with an internal code that we use to identify the shipper named United Package. And we refer to that code as the organization ID. And that's really all we need. The rest of the information required for this role link is configured out in the administration console. So let's go take a look at that. First of all, let's take a look at the configuration of the role links. Okay, here we have the role link from our orchestration. You can see here in the title that we're looking at the shipper role link that we just saw in the orchestration. Let's remove the parties that are already configured so you can see what it would look like to configure a new role link. Okay, assuming that we have the parties defined, we need to enlist the parties in our role link. So here's a list of all of the parties defined in this BizTalk group. Let's select the two that apply to this role link. Okay, you can see that we have added them to the list, but there is still another step that we need to take. Each of these parties could have one or more send ports associated with them. So we need to specify which send port should be used to communicate with each party. So let's bind a send port to each party. Okay, this gives us a chance to select which of the one-way send ports that is associated with the federal shipping party that should be used to communicate these messages. Federal shipping has only a single one-way send port associated with it, so we'll select that one. And now we need to do the same thing for United Package. Okay, if either of those parties had multiple one-way send ports assigned to them, we could have selected from any of those send ports. Okay, our role link is configured. Okay, let's take a look at the send ports in our application. The send port listed at the top is our dynamic send port, followed by the two static send ports that we've named after our shipping vendors. Now let's look at the definitions of the parties. You can see that the same parties are listed here as those that we saw in the list when we were configuring the role links. Here we have the United Package party, and each party can have one or more profiles associated with it. A profile could represent an individual within that organization, or it could represent some business unit. Profiles give us a way to organize the various collections of configuration settings that we need to communicate with a trading partner. Let's take a look at the default profile for United Package. Alright, we can see the name. It's possible to enter some name-value pairs to describe this profile, but those really aren't used by the application in any sense. They're just here for annotation purposes. Each profile is going to have a collection of identities. So this relates to that organization ID that we saw the orchestration make use of when it set the destination party on the role link. So the runtime is going to search all of the parties that have been associated with a role link, looking for the organization ID values, and then looking for the one with the value of UP. Now when we look at the United Package Party, we can actually see the send ports associated with it. By the way, you can ignore the fact that organization ID is listed a second time under additional properties here, because again, those are simply for annotation purposes, and they are ignored by the runtime. And this is where you can see the send ports that have been associated with United Package. So we could assign any number of send ports to the United Package Party, and then they will be included in the list of options when we're configuring our role links. Okay, let's go run this orchestration and see if it routes the messages as we expect. Okay, we have two sample files here, one that represents an order that will be shipped within the UK, and a second one that will be shipped outside of the UK. So let's send each of these messages through. We expect that this message will be routed to the United Package folder. Okay, we'll drop a copy in. BizTalk has picked it up. We can see that nothing has shown up in the federal shipping folder. The message appears as we expect. Okay, let's send through the message that represents the order to be shipped outside of the UK. When we send this email to our local machine, we expect that the SMTP service will store it in the SMTP drop folder. Okay, so that folder is empty. BizTalk has picked up the message. Okay, the message has arrived. Let's open it and see if we can find the attachment. All right, there we have it. The message was sent to Alice at our local machine. We can see that the subject line matches the text set by the orchestration, as well as the text in the message body. Now let's open the attachment. All right, there it is. That's a copy of the order message. And this is where it could have made sense to use an InfoPath form to make this data more presentable to the user. Okay, so hopefully that gives you a sense of what it takes to create a dynamically bound send port and to configure a role link with its associated parties. There is one more thing that we need to think about with regard to orchestration port bindings. When we need to implement an orchestration that will be receiving multiple messages that are related, especially if we don't know how many of these messages the orchestration will be receiving, or if we don't know the order in which those messages will be arriving. We need to rely on a little bit of extra help from the orchestration runtime in these types of situations. And because of that, we need to know how to configure the receive shapes in our orchestrations to handle these types of scenarios. I'm going to start with a review of what correlation is and how it works. And included in that is a review of the types of orchestration subscriptions that we have seen. And then I'll show you a couple of ways to lay out orchestrations to receive multiple related messages, which are otherwise known as convoy messaging patterns. All right, it has been a little while since we first talked about correlation. So let's do a quick review of the basics before we go any further. So in this picture, we have a couple of orchestration instances running. Each of them is processing a different order and they each need to send their respective order out for approval. So, when the first orchestration reaches that point, it will submit the approval request to the message box, and in the process, it will initialize a correlation set with the value of the order ID. And as a result, an instant subscription will be created, and when the approval response comes back for order number 5, that message will be delivered to the receive shape of this orchestration instance. In the meantime, while the first instance is waiting for a response, our second orchestration instance sends out a request for approval, and another instant subscription gets created, this time for an approval response with order ID equal to 7. When the response for order number 7 does arrive, it will be delivered back to the second instance, and then when the response for order number 5 arrives, it will be delivered to the first instance. So we learned that the orchestration runtime makes use of two different types of subscriptions. The first being an activation subscription, and when a message arrives that fulfills an activation subscription, the runtime will create a new instance of the corresponding orchestration, and that subscription is registered with the message box when the orchestration is enlisted. And then an instant subscription is required when we use correlation, and you could say that it is a finer-grained subscription. It includes additional conditions so that an incoming message can be delivered to the specific instance of the orchestration that is waiting for it. And these types of subscriptions are registered when an orchestration initializes a correlation set. That combination of activation subscriptions and instant subscriptions works pretty well when the correlation set is initialized by a send shape. That sequence is pretty clear-cut because, after all, it doesn't make much sense to talk about receiving a response before a request was ever sent. It gets a little trickier, however, if the correlation set is initialized by a receive shape. And that might sound strange at first, but if you just consider for a moment what that means, it turns out to be pretty useful. You can see a couple of simple scenarios illustrated at the top of this slide. On the left, you can see a receive port that is connected to two different receive shapes. In this case, the orchestration receives a message and starts running, and then it continues to pick up new messages of the same type until some loop condition is met, and then it continues on. This orchestration could be managing something like an auction, where it is initialized with a message that represents a bid, and then it continues to collect bid messages until the auction ends, and then it can move on and determine the highest bidder and send out a notification indicating who won the auction. On the right-hand side, we have an orchestration that is waiting for exactly two messages, but it doesn't know the order in which they will arrive. We might be waiting for two different systems to finish processing some data, and we know that they will both send us a notification when they complete processing. We could specify a filter on one receive shape to wait for a message from one system, and then specify a filter on the other receive shape to wait for a notification from the other system. And when the orchestration receives both of those messages, it can continue processing. Perhaps it will merge the content of those two messages. So these are two examples of convoy patterns. The one on the left is called a sequential convoy, and the one on the right is a parallel convoy. Now, in both cases, the potential exists for multiple messages to arrive at exactly the same time. And if the orchestration runtime simply went and carried out business as usual, it could create two instances of an orchestration, not realizing that those messages should have been processed by the same instance. Fortunately, the orchestration engine knows how to accommodate these types of conditions. We just need to make sure that we set up the receive shapes properly so that it can do its job. So let's look at these convoy patterns one at a time. Sequential convoys are useful when you know that your orchestration will be receiving multiple correlated messages, but you don't actually know how many messages the orchestration will receive, such as bids for some given item that is up for auction. In the case of an auction, you know that the orchestration should continue to wait for messages for a specific period of time. In other cases, the loop condition might be based on values read from the messages. We might have an orchestration that is responsible for consolidating shipments, and it might receive order messages correlated by a region code, whether that's a country or a state or some other code. And when the total shipping weight for all of those orders reaches some predetermined amount, the orchestration can move ahead and make the arrangements for the shipment. If you include a listen shape within the loop, you could accommodate both types of conditions. The shipping orchestration might wait for messages, but if 24 hours have passed since the first order arrived, we might want that orchestration to go ahead and ship whatever it has accumulated for that region so far. When you implement a sequential convoy, you need to set it up so that all of the messages will arrive through the same receive port. If all of the messages are of the same type, then that would be known as a uniform sequential convoy. If the orchestration will be receiving correlated messages of different types, then that's known as a non-uniform sequential convoy. And to handle that case, your receive port type will need to define an operation for each of the message types. That way, the orchestration runtime can continue to coordinate the activity for a single port, in spite of the different message formats. All right, here we have a picture of a very simple sequential convoy. This convoy is designed to handle messages that are all of the same type. And we know that because the receive port defines only one operation. Now, even though this is a very simple convoy, it's enough to illustrate the 3 steps that you need to take to configure a sequential convoy. You'll need to configure the first receive shape to initialize the correlation set for these messages. Then, you'll need to configure any of the other receive shapes that will be participating in this convoy to follow that correlation set. And then finally, you'll need to configure a loop condition. And that condition should evaluate to true as long as the orchestration should continue to wait for new messages. And then, when the orchestration has all of the messages that it needs, and the loop condition evaluates to false, the orchestration will be able to break out of the loop and move on. When it comes to parallel convoys then, we know how many correlated messages the orchestration will be receiving. We just don't know which one will arrive first. One of the other differences is that it can receive messages from more than one port if necessary. And then, like the sequential convoy, the parallel convoy can handle messages of different types. The key constraint then is that you need to know the number of messages up front, because each of the receives will be implemented within a branch of a parallel action shape. And it's actually this type of situation that motivated the design of the parallel action shape. You're free to use it for other purposes, of course. Just don't expect multi-threaded behavior, because it won't do that for you. But it will coordinate all of these receives. And wait until each of the receive shapes has accepted a message before it will allow the orchestration to continue processing. Now, when it comes to configuring a parallel convoy, you can see that this one will be receiving 2 messages of the same type. But again, we could set this up so that each of those messages arrives through a different port. And they might be of different types. We just need to be able to define a correlation type that applies to both messages. Looking at the parallel action shape, you'll need to add 1 branch for each of the correlated messages that will be arriving. And then you'll need to configure the first shape to initialize the correlation set. And after that, you'll actually need to configure each of the other receive shapes to initialize that same correlation set. And that might sound strange at first, but that's one of the things that the parallel actions shape is designed to handle. It will initialize the correlation set when the first of these correlated messages arrive, and then the other receive shapes will automatically switch to follow that correlation set. Along with that, we need to set activate to true on each of these receive shapes. After that, we can depend on the parallel actions shape to wait until all of the messages have arrived. and then our orchestration can make use of that data when it continues on. In this demonstration, I will show you two orchestrations, one that implements a sequential convoy that accepts two different types of messages, and the other one implements a parallel convoy that accepts the same two types of messages. It just doesn't make any assumptions about the order in which those will arrive. Okay, so we have a couple of orchestrations in this solution. Let's start off by looking at the sequential sample orchestration. Alright, here is the initial receive shape. It accepts a message via the submit billing operation on our orchestration's receive port. Let's take a look at its properties. First of all, you can see that this is an activating receive shape. So when a new billing message arrives that does not meet any of the current instance subscriptions, the runtime will create a new instance of this orchestration to process this billing message. Now the send initial audit is going to send a copy of that bill via the audit billing operation of the orchestration send port. So there's nothing out of the ordinary with the configuration of this send shape. Now the orchestration is going to remain in this loop as long as it continues to receive billing messages that apply to this order. Once it receives a shipping message, then it will break out of the loop. So the orchestration simply has a variable named loop flag, and that is initialized to true, and it will remain true until it receives a shipping message. Now you can see each of the branches of the listen shape starts off with a receive shape. The branch on the left is waiting for new billing messages that serve as updates to the initial billing message. So if a shipping message arrives, the orchestration will execute down the right-hand path and encounter this expression shape, and that's where the loop flag variable will be set to false. Now you can see each of the branches of the listen shape starts off with a receive shape. On the left-hand side, the receive shape is waiting for new billing messages. Let's take a closer look at that shape. The first thing to notice here is that the activate property is set to false. And that's because the orchestration would already be up and running by the time it reaches this receive shape. And then the second thing to notice is that this shape is configured to follow the sequential customer correlation set. Let's look at the receive shipping shape. You can see that this receive shape is configured in exactly the same way. Now we know that if these receive shapes are following a correlation set, it must have been initialized somewhere, and that correlation set then is configured to be initialized on the initial bill receive shape. Okay, so we can see that this orchestration is going to receive a billing message and send a copy of that off for audit, and then it is going to listen for additional billing messages, and at the same time it is listening for a shipping message. And as it receives any of those messages, it will send those off for audit as well. And then when it does receive a shipping message, it will break out of the loop. Okay, let's go see how this performs at runtime. Alright, so we have a set of sample messages here. Let's initialize the orchestration with a billing message. And now let's go to the group hub to see the tracking information. Okay, you can see that we have one running surface instance and that it is dehydrated. And this is in fact an instance of the sequential sample orchestration. And there is no error information, it is simply waiting for additional messages. And we can see that it has consumed one message so far. Alright, let's send the rest of the billing messages through. Okay, we can see that the 4 billing messages have been sent to the audit folder. Now let's visit the Group Hub one more time to view the tracking information. Okay, we can see that the instance of the orchestration is still running. Now let's send the shipping message through. Okay, at this point, the orchestration should have processed and completed. All right, and as expected, it no longer appears in the query results. And we can see that a new message has shown up in the audit port. Let's delete all of these. And now I'll demonstrate the condition in which an orchestration can leave so-called zombie messages in the message box. I'm going to run this batch file, and it will send one message to initialize a new instance of the orchestration. And then after pausing, it will copy all of the remaining messages, including the shipping message, at the same time to the file in folder. Okay, so the initial message has been sent. Now let's send the remaining messages. All right, let's see what happened. We can see that there are no orchestrations listed. Let's query for tracked service instances. Here you can see an instance that was suspended. And this message is stating that the orchestration completed without consuming all of its messages. And it's stating that the messages that it never processed have been suspended. And here it's showing that there were 3 messages delivered to this orchestration, but it had already received the shipping message and had moved on. And all 3 of these were instances of the billing message. Okay, these will remain here. There's not much we can do about these except to terminate them. All right, so that instance is no longer running. Let's go ahead then and look at the example of a parallel convoy. Okay, you can see here a parallel action shape, and each branch starts off with a receive shape. The branch on the left is waiting for a billing message, and the branch on the right is waiting for a shipping message. And as each message is received, it will be sent off to the audit port. And the orchestration will complete only when it has received one of each type of message. And you can see then that the billing receive shape is configured to initialize the customer correlation set, and it is also marked as an activating receive shape. And you can see that the shipping receive shape is configured exactly the same way. If we needed to receive additional messages, we could simply add a new branch for each additional message that we needed to receive. Okay, let's test this orchestration. I'm going to unenlist the sequential sample orchestration and then start the parallel convoy orchestration. Okay, let's delete the messages from the audit folder. And now I'll copy an instance of the billing message in first. And we can see that we have one running service instance. And this time it is an instance of the parallel convoy orchestration. Now let's send a copy of the shipping message through. Okay, the orchestration should have completed. And as expected, it no longer shows up in the report. Let's try that in the opposite order. Let's send the shipping message through first, followed by the billing message. Okay, once again we have an instance of the orchestration. And now the orchestration should have completed. So our parallel convoy orchestration is working as expected. These were obviously very simple convoy orchestrations, but any sort of convoy that you implement will boil down to one of these two types. And the configuration in those cases will be no different than what you've seen here. You will be working with the Northwind solution in this lab, and you will be modifying the route order orchestration to send out a shipping request and receive an acknowledgement back. So you'll need to set up correlation for that. And then you're going to deploy that orchestration and bind the send port for the shipping request and the receive port for the shipping acknowledgement to corresponding physical ports. And that will give you a chance to run a preliminary test to make sure that your correlation is working correctly. After that, you're going to revisit this solution and start working with an orchestration that can handle the shipping automatically. And that new orchestration will make use of a role link to direct their shipping request to the correct vendor. And then in the administration console, you'll define 3 parties so you can actually make use of the role link. And then you'll redeploy the solution and run a test to make sure that your role links are working properly. And then you'll revisit the solution one more time and modify the route order orchestration so that it can call the shipping orchestration by using direct binding with the shared port.